right, everybody, welcome on in. Sort of continuing through the material here. Oops, let me change a setting here in chat and Zoom. Okay, so I will be showing you some stuff today, so it's up to you. Those of you who are in Zoom, you're welcome to stay in Zoom, but you obviously won't get to see as much. So however you want to do it, totally fine. We're going to go over some material. So remember last time I talked about some stuff seemed to be missing. So it wasn't missing, but I'd had it due a couple days earlier. That's why it wasn't showing up under the upcoming assignments. So I had said I might add a couple of assignments into, where was it? Somewhere. One of these assignments I said, oh, I'm going to have to add a couple more things. I didn't, because I had already made the assignment that I thought I had made, right? That's what, remember, I was kind of confused. Like, wait, I thought I added that already. So I had, but the assignment was due a few days earlier. Well, it's kind of weird that I would have the assignment due before I talk about it in class. So I just extended the date of that previously due assignment. So from the looks of it, most of you had gotten through it and were fine and understand how to do it. So that's great. That means we're moving things along successfully, so that's good. If you do want to go back and work on it more or look at it or whatever, you can do that because I extended that due date. So that's all. So as far as the existing assignments, you didn't have any more work to do. I just reopened an old assignment because now that I covered the material, the argument could be made like, well, now I can go work on it. Yeah, sure, go work on it if you still need to. So you can do that. Okay. So, that's all good. And some of this is important stuff that's going to come up again. We didn't really have time to cover it in this class, but some of like this visual composition of functions and understanding the connection between the graphs of composition of functions and stuff like that will play a role for some of you that end up in college algebra or pre-calculus. So if that's you, just kind of be aware you're going to see those topics again in the future, and you're going to have to sort of work with them. Okay? So with that said, let's move ahead. I think we talked about schedule and everything like that. So let's see. We meet today. What is today? Wednesday. So we meet today, and then what? Twice next week, right? Because Wednesday's still regular schedule. Yeah. So we have 3 class meetings, including today. Today's the 1st. We'll meet next week on the 6th and the 8th, and then after that it is finals week. And just remember, it's a little harder to get a hold of me on finals week because we don't have normal office hours and stuff like that, because once we start finals week, the schedules just kind of go out the window because everyone's meeting at different times, and everything's just kind of crazy, and some classes have concluded, and so they wouldn't come to office hours anyways. But if you need to get a hold of me, try to get a hold of me, email me, whatever we need to do. But don't wait till the last minute. If you try to get a hold of me at the last minute, we're probably not going to connect, right? Because I probably won't get your email. I won't probably be checking email at the instant that you're having your panic attack because you're trying to meet the deadline or whatever. So, don't wait till the last minute. Early next week, there will be a practice test released. And then the test will be made available to you so that you can finish. You can either finish things up if you think you're ready to finish things up. You can finish things up a little early, or if you need more time to study, you have more time to study. You can do the thing that works for you, the thing that makes sense for what you're doing. Okay, so I am still recovering from a cold. My throat is a mess today. My morning 8 a.m. class, basically by the end of class, I could barely speak. So then I had an hour break for office hours. So I'm speaking a little bit better, but it's entirely possible that by the time we approach the end of class, I will probably be unable to speak again just because my throat is a mess between coughing and sore throat and all this kind of stuff. So so just kind of be patient with me a little bit. Okay, so the thing I want to show you, we have quite a few things to get through, but I want to show you inverses quickly to at least go through that. Inverses are very important. Again, if you end up in a college algebra or pre-calc class, you're gonna want to be able to look at graphs and tell which ones are inverses. There's some interesting behavior about inverses, which we'll cover really quick. But inverses are hugely important functions. In fact, let's just go with it right now. Let's go Desmos. Okay, so before I even get into what an inverse function is, I want to cover this graphical part because you just want to have seen it. So let's take something like so these two things aren't, well, actually let's make this way. Here we go, like this. Do you notice there's a symmetry of these two graphs? There's the blue function and there is the red function. And these two things together make a symmetry. Symmetry, there's numerous different types of symmetry. It just means that there's a pattern that gets repeated essentially at some point. You can have linear symmetry, which is what most people think of. If you have a drawing on a piece of paper and you fold that piece of paper up in half and half of the graph lines up on the other half, then you have a type of symmetry. So for example, y equals x squared. Here we have a parabola. If this was a piece of paper and I folded it down the middle, this left half would line up perfectly on the right half. That's called symmetry. That's linear symmetry. There's a line where if we folded the paper on that line, the two sides would match up. There's many types of symmetry, right? I've heard people get into arguments about, well, someone will say, oh, look, this has this type of symmetry, and someone's like, that's not what symmetry is. There's many types of symmetry. There's rotational symmetry. There is linear symmetry. There's symmetry with respect to a point. So don't get too hung up on the definition of symmetry. There's numerous times, and usually you kind of know it when you see it, right? If I show you some type of symmetry, you're going to go, oh, okay, I see that's a type of symmetry, sure. So like this, fold this paper in half. The left half lines up on the right. We get a symmetry. We have a symmetry here between these two types of functions right here. Now, it's not the same symmetry we looked at a minute ago, because if I fold this paper down the middle on a vertical line, well, this part of the blue line is not going to line up on this part of the red line. That's not, right? This thing won't line up on itself. There is a rotational symmetry here. If you take the point here and you just rotate the thing 180 degrees, this piece will now be this piece, and this piece will now be this piece. So there is a rotational symmetry, but that's not even the one we're looking at. Some types of things can have more than one type of symmetry. Can have numerous types of symmetry. It's interesting that so many people misunderstand symmetry because it's a huge area of mathematics. When you get past calculus and you get into kind of like the real mathematics, symmetry comes up a lot. You create these whole systems for describing symmetry, which is actually really interesting because it comes up in chemistry and physics and all these different places. Like symmetry in chemistry is important. If you have a new molecule and you want to know, is it symmetric in certain types of ways, you have to be able to describe that type of symmetry, that really complex symmetry. But the important symmetry here is actually, if you notice, if I take the line y equals x, so this is starting to get kind of complicated, but just look at the blue graph and then look at that purple line. So instead of before, it was kind of simple. We just had that vertical line on the parabola and we folded the paper up on itself. What if we took this piece of paper and we folded it on the purple line? So at the slant, well, what would happen is this piece here would kind of come down here, and this piece here would go up here. And in fact, what you would get is you would get the red pieces. So we have these two different functions where if I fold this purple down, the blue and red line up on top of each other. We get a type of symmetry. Okay, this is one of the consequences of inverses. So we can see that the red and blue functions are inverses because they have this symmetry with respect to the line y equals x. You might go, why y equals x? Again, if you know, on the other side of calculus, when you learn about these symmetries, you'll learn why the line y equals x is so important. There's a reason in algebra we teach it to you as the identity function. It's this whole like big thing that we're sort of ready to dive into. But you can see it graphically when you look at this. You can see the symmetry, and you know when it's off. Watch, I'll just change this a little bit, and your brain's going to instantly get uncomfortable. Like you go, that doesn't look right. Something looks off. There, doesn't look right anymore, right? There, that doesn't look right anymore. Your brain knows, yeah, there's a symmetry that's not, it's broken. It's not working anymore. But when we have this, you go, okay, yeah, I can see the symmetry. So that is a nice quick way of visually determining if two things are inverses, is if you draw the line y equals x, do they have the symmetry of each other over that line y equals x? If it looks like this, those two things are inverses. If it looks like this, something's wrong. They're not inverses. Okay, so that's convenient because verifying that two things are inverses is hard, takes some work. But if you can just put them on a graph and look at it and go, nope, those are not inverses, that saves you some time, right? So keep that in mind. So that's the graphical part of things. So how do you verify that two things are inverses? Well, our definition for inverses is going to say that two inverses, if two functions are inverses, and I haven't even told you what inverses are yet, we'll get to that in just a minute, but if two functions are inverse and we compose them, so the thing we talked about last time and that many of you have actually completed the homework for, composing two functions, if you compose two functions and your result is x both times, so you compose f with g and you compose g with f, and both times it simplifies down to just the term x, those two things are inverses. So you could imagine, those of you, which is most of you, who have done the composition homework, those problems sometimes were kind of a pain, right? Like sometimes they're not too bad. Sometimes they could get a little bit tedious. Like the one I showed in class, you're like squaring polynomials and doing all this stuff. It's not terrible, but it's not fun. That's a lot of work. Or just throw it into a graph on Desmos and look at it and go, no, those are not inverses of each other. So you kind of have the algebraic way when you want to be 100% sure about what you're doing, but then you also have this visual way when you're going to be like pretty sure. Like you can, in an instant you can tell like, yeah, I think those are probably inverses of each other. Okay, so inverse functions, hugely, hugely important. And the whole reason we're introducing them is because we're about to introduce the definition of logarithms. May or may not get to that today, depending on time. Logarithms are defined to be the inverse functions of exponential functions. So the whole reason we create logarithms is because we need inverses for exponential functions. Okay, inverse functions, hugely important. I remember when I was in grad school, like they didn't really come up in the area of research that I was doing, but there were other people who like, they would spend a whole month finding one inverse to like a specific problem, like a really complicated one, and they'd be trying to get that inverse, but they would take like forever because it was a big complicated one, but it was super important that they find it. Like in some cases, once they could find that inverse, it would help them solve the whole problem that they were working on for this big project. So inverse functions allow us to reverse the roles of the variables and ask the question in a different way. Okay, so here's a basic example I can give you. You're about to start learning about exponential functions, and when you do exponential functions, there's all sorts of problems out there, huge amounts of problems that are exponential problems that you can start calculating. Growth rates of things, growth rates of bacteria cultures, growth rates of populations of humans and animals and plants and all sorts of growth rates, interest rates, right? You have a bank account and it's earning 2% interest. You use exponential functions to calculate money, stuff like that. So probability density functions, which are ways that companies and researchers and everyone uses to calculate probabilities of certain events. These are exponential functions. So but you can only do the problem one direction if all you have is the exponential function. So like from the financial problems, okay, so let's just say you inherit $10,000 and you want to go just have fun with it, but you're like, I should probably be responsible. I should probably just stick this $10,000 in a retirement account, let it grow for the next few decades, and then it'll be a nice big pile of money when I am retired and I kind of need that money. Well, using exponential functions, you can calculate what that thing's going to grow to. You say, okay, I got $10,000. It's getting 2% interest per year. It's compounded monthly. What's it going to be 25 years from now? And you can calculate that, and that's a fairly straightforward thing to do. But sometimes that's not really the question you want to answer. What you might want to answer, and this is literally how they, if you go talk to a retirement planner, they'll walk you through what I'm explaining right now, is instead of being able to say, well, I've got some money now, what can it grow to in the future? Sometimes it's helpful to turn that question around and say, well, when I retire at 65, this is like a theoretical situation I'm just making up, but say there's an individual, they want to retire at 65, and they want to have some certain amount of money in an account to retire on, maybe $500,000. Okay, so I need $500,000 at the age of 65. What do I need to save now in order to get to that point? Okay. So that's a different question, right? It's different than saying, well, I have some money now. What's it going to grow to in the future? Versus saying, I want to have a specific amount of money in the future. What do I need to do now? See how those are different questions, and they would help you approach the problem differently? Well, one of those requires an inverse. The other, like the first one, that is less helpful. I've got some money. What's it going to grow to in the future? That one's easy. But asking, okay, I need $500,000 at 65. What's it going to grow to? What do I need to put away now to grow to that? You have to have an inverse function in order to do that. That's actually one of the reasons we create the logarithm. And just a heads up, because you're going to start be doing some of these financial problems. That might seem like a lot where you're like, what, $500,000? Why would you need $500,000 when you're retired? Because hopefully when you're retired, your house is paid off and stuff like that. What you have to realize, depending on the type of retirement accounts you have, is most people in retirement are essentially living off interest. Right? So you have to have enough money in an account that you can live off the interest, because otherwise, like $500,000 seems like a lot of money. But if you're retired and you have no income, maybe you get a little Social Security or something like that, you'll blast through that $500,000 faster than you think. 7, 8, 10 years maybe, right? At the most, it'll last you 10 years, and then it's gone, and then you're poor. So what you're supposed to do is try to live off the interest and the amount of money that you've accrued. Well, interest rates, since many of you, interest rates have been bad your entire lives. Basically, once 2008 financial crisis hit, workers, people like us who have to work, we can't get good interest rates on accounts anymore, which means you're maybe getting, if you're good, you're maybe getting 2-3% at the most. So, what does that mean? That means for every $100, you're going to get $2 of interest. So if you think about it from that perspective, you kind of got to have a pile of money that you're sitting on to earn enough interest to get yourself through the year, right? So for every $100,000 you have saved away, well, if you're earning 2% interest, that means you're only getting $2,000 off that $100,000 each year. So you kind of want to look at it in that perspective. The other way to do it is to make sure you get yourself a job that has a pension, but those are rare because the unions have all been squashed. Very, very few people work for unions anymore, so it's kind of hard to get those jobs. So those of you, especially if you're on the younger side, it is not too early to start saving for retirement. One of the rules of thumb for retirement is every 10 years earlier you start saving for retirement, you only have to save half as much because it has that extra decades to grow. But some of the stuff in this country, the way we do it is that what do they say? The average individual in this country has $0 saved for retirement. That's not good. That's sort of an impending disaster we're going to be facing in the coming decades. So you just be aware of retirement. Don't ignore it. You think about it. And it's relevant. I bring it up because you're going to see these types of problems as you're doing these exponential problems. Those of you who are going on to college algebra, pre-calc, you'll do these financial saving types of problems using exponential functions. Okay. All right, so that's enough justification for why inverse functions are important. Let's go through and figure out how to calculate one. So let's see, where did I have, which, I forget which one these, okay, that's, inverses with logs will come a little bit later in here. I thought there was a simpler one to start off with if I'm looking here. Okay, so a couple things to know. What does this mean? This f with a -1 on it? What does an exponent of a -1 mean? Do we remember that? Yeah, we know what f with an exponent of -1 means. However, that's not what this is. Okay, so I bring that up because there's always one or two students who think this is an exponent. This is not an exponent. This is just a notation that we put on the function f. So you can have negative exponents. We did that, I don't know, a few weeks or months ago. But this is not a variable. This is a function. So when you see f to the -1, where it looks like that, it's not really an exponent. It's a superscript. It just means it's up in the air like that with that little -1. That just means inverse. Okay, so whenever you see this here, f with a -1 superscript, that means that it is the inverse of f. So f and then f with a -1 up here, that means these two things are inverses. So what are they telling you? So they say, if we define this function f to be 4 times the cube root of x, find f inverse. They're telling you to find the inverse. So let's look at that one. 4 times the cube root of x. Okay. So if we take f of x equals 4 times the cube root of x. Let's see, is that right? 4 times the cube root of x. Okay. So they want us to find the inverse. So the thing is, for inverses, there's 4 steps that you do every time. Like, you'll have different inverses, and some inverses are super easy to find. If you want to find the inverse for a line, it's like really easy. If you want to find the inverse for a certain type of polynomial, might be a little harder. Some things don't even have inverses, right? So sometimes it's impossible to find the inverse because it doesn't exist. So don't spend too much time trying to find an inverse. It may not exist for that particular problem, right? If you're like, I keep doing this problem, maybe there is no inverse. That's a possibility. So what are those steps then? What do we do? Okay, the good news, of the 4 steps, 3 of them are like trivially easy, like ridiculously easy steps. You're almost not doing anything for 3 of those steps. One of them, that's the piece that varies. For lines, step number 3 is very easy. For certain like rational expressions that we dealt with a chapter or 2 ago, step 3 is like ridiculously hard. So every problem, finding the inverse is a little bit different, okay? So step 1 is we replace f of x with y. Okay, so f of x and y really mean the same thing in function notation. Whoops. Should look like that. When we use function notation, we use f of x. When we're talking about specific points or equations, sometimes we use y. So it really depends on what you're doing, whether you use f of x or y, but they really mean the same thing. The y is just the y value associated to x, but what does f of x mean? That means we took x and plugged it into the function f. Well, that gives us the y, right? So see how up here it's written as f of x? We just rewrite it with a y. So this is one of those like steps that's so easy it's silly. We just write this as y equals 4 times the cube root of x. All right, pretty straightforward, right? All I did was take this f of x and rewrite it as a y. Super easy step. Okay, step 2. We're going to swap all x's. Swap all x's and y's. It's always weird writing a variable as a plural. We're going to take all our x's and y's and we're going to just switch them with each other. So in other words, I'm going to rewrite that line right above, but wherever there's a y, I'm going to write an x. Wherever there's an x, I'm going to write a y. Okay, so that becomes, so another super easy step becomes x equals 4 times the square root of 3. The cube root of x is what I meant to say. This is not right. This should be. Okay, that looks right. So see, I turned that y into an x. Oops, but I didn't turn the x into a y. That's right there. Okay, so the x's got turned into y's, the y's got turned into x's. So far, easy, right? Both of these steps, like, easy. I'm just supposed to turn my f of x into a y and then switch my x's and y's. Okay, this is easy. Now it's the step that can sometimes be easy, can sometimes be hard. Step 3, we're going to solve for the variable y. If you're, like I say, if you're dealing with some line, y equals 2/3 x minus 7, solving for y is going to be really easy. If this is a rational expression where you have y's in the top, y's in the bottom, it gets harder to do. Okay, so for us, let's see, I'm going to solve for y. Let's see, so what am I going to do? Looks like I'm going to cube the entire equation. So doing that should give me x cubed equals 64y. Now, how did I do that? Well, if I cube x, I get x cubed. That's straightforward. Okay. The 4, we have to cube that using our exponent rules. If we cube the thing on the right, both pieces get cubed because they're connected by multiplication. So it becomes 64, which is 4 times 4 times 4. And then y, because y cubed is y. If anyone doesn't understand what I just did, let me know. Okay. Let me know how that works for you. Okay. Now we solve for y, so it looks like we're just going to divide by 64. So let's see. I don't remember that being... Oh, they were writing a little bit differently than I did. So we're going to have to adjust how our problem is written. So but that's okay. This is a thing you have to do sometimes, is you get an answer, but it doesn't quite match the way they have it displayed, and you got to figure out, does my answer match one of theirs? And the answer is yes. So what they did, so x cubed over 64 equals y. So you look around for that and go, I don't see anything that looks like that at all. But it looks like it's this top one. Because look what we could have done. We could have solved this a different way. What if I had divided by 4? That would give me x over 4. And then when I cubed both sides, we'd get x over 4 cubed, this is just a simplification of that. So what I have written here is a simplification of this first one right here. So this is going to be our answer that we're going to go with in just a second. Okay, but what about step 4? I said there was 4 steps. Yeah, step 4 is easy again. What you do is you replace y with f inverse of x. So where your y is written, you just write the inverse of x notation back in there. So steps 1, 2, and 4, super easy. Step 3 can range from easy to impossible, depending on the problem that you're working on. But for us, it's going to be this one right here. So then, then when you do these problems, you kind of see like, oh yeah, in this problem, they want me to do it this way. So you'll pick up on the, how they want that problem simplified. So you can see what they did. They did it slightly different than we did. They divided by the 4, and then they cubed both sides. That's how they got x over 4 cubed. For us, we had x cubed over 64, which is how you would simplify this fraction. I'm not sure why they didn't simplify it, but so that's fine. So those are the steps for finding an inverse. It's the same 4 steps always. Now, the step that can vary is this one, solve for y, because depending on the problem that you're given, that solve for y can be a totally different ball game. So you can't really memorize that step, because all I have to do is, okay, well, now I'm giving you a polynomial. Now try it. And it's like, okay, well, the algebra is different than I did for the line. So the basic overall steps, those 4 steps stay the same, but just realize 3 is going to vary a bit depending on the problem that you're trying to find the inverse of. Okay? All right. So with that one under our belt, let's jump into logarithms. So for the sake of time, I'm going to a little bit skip exponentials. I'll talk about it a little bit along the way, but we just don't have a ton of time for what we have left in class. And usually people are fine with exponential functions. It's logarithms that they find really confusing. And so I want to cover the logarithms, because that's an important one that a lot of people don't get the first time. Did I close Desmos? Where'd it go? Okay, so we can look at things graphically. So here is an example of a exponential function. Okay, this is what your exponential functions generally look like. It looks like they come down and become a straight line down here. It straightens out, but it's never perfectly straight. It's approaching this line, but never quite touching it, weirdly enough. Like, think about plugging in negative 100. 2 to the negative 100 becomes 1 over 2 to the 100, which becomes 1 over a very, very big number, meaning it becomes a very small number. So they're just tiny, tiny numbers between the line and the curve right there. And then they go up like this. Well, exponential functions come up all over the place. They come up in every area of research. They come up in all sorts of business, finance, growth rates, probability functions, all sorts of stuff. Hugely important. So, like I mentioned earlier, we want to have the inverse to these. And we define the inverse, and then we call it the logarithm. So the inverse of an exponential is the same based logarithm. So when I do this, see, we get that symmetry, right? Remember the line y equals x? We got it right here. Yeah, if I folded this paper right on the green line, the red curve is going to show up right on the blue curve. Sorry, I'm kind of at that same point. The last 15 minutes in the morning class was rough trying to speak. So see how we get that same symmetry? So we can see that this exponential base 2 function and the logarithm base 2 function are inverses of each other. And I get you don't know what a log base 2 means yet. That's okay. We'll talk about it. But these two things are inverses. That's the whole reason we create the logarithm. I myself was confused when I first learned logarithms. Like, it just seems like we're making stuff up now. What is going on with these logarithms? It's weird. And it wasn't till later where I fully appreciated, oh, we need the inverse function for this other really useful function. So we just constructed it. We constructed this thing to be the logarithm. So while it seems artificial, yeah, that's because we made it. We made it to be the thing we wanted it to be, which is the inverse of the exponential function. And the notation gets really weird. I know a lot of times for students, half the problem is learning the new notation. Well, logarithms have a definite weird notation. But here's what I'll say. My students that master the notation and understand the basic definition of the logarithm, which I'm about to show you, get much farther in these chapters than the students who don't. So it's worth your time. Invest a little time in trying to understand the notation of the logarithm, and you're going to do a lot better working through a lot of this material. Okay, so what is a logarithm? All right, so I'm going to have to look over to make sure I don't mess up this definition. Right, so if we have some conditions, we have this value b, which is going to be our base, has to be greater than 0, and also b cannot be equal to 1. So we have an exponential function. The base is greater than 0. It's not equal to 1. Then, let's see, f of x equal to... Actually, this is kind of a weird definition. This is not how it's usually written. Right. Let's write it this way. X equals b to the y means y equals log base b x. I should make that like that. Okay, so here's your basic definition. I'm sure it doesn't mean a lot to you at the moment when you're first looking at it, but let's try to make sense of it. So we're saying that b has to be greater than 0 and not equal to 1. So all that means is any base we use for an exponential or logarithm should be a positive number not equal to 1. If you use a negative number for your base, you get really, really weird behavior. And it can be kind of interesting to study those functions, but they don't come up in the real world as much as exponential functions do. Exponential functions come up all over the place. Those other weird functions where you'd have a negative number raised to a base, cool functions, you're not going to find them nearly as much as you do exponential functions. So exponential functions and logarithms are important because they get used so many different places. Okay, so what do we have here? Well, our original function would be something like y equals b to the x. So the inverse would have the variables switched. Remember when we swapped the x's and y's when we were finding the inverse? That's literally what happens with your x's and y's. If you take the points for a function and you just switch all the x's and y's in the points, you get the inverse. So that's literally what we're doing in an inverse, is we're switching all the x's and y's, which makes sense. If a function turns 2's into 3's, the inverse better turn 3's back into 2's, because inverses are supposed to undo the original function, right? So if we have something as x equals b to the y, we interpret this as y equals log base b to the x. And I know people still look at this and go, that doesn't help. That doesn't, like, I still don't get what's going on. What you want to be able to do is look at these two forms and move back and forth between them, because you're going to have times where you have something written as a log, and the easiest way to change it is to turn it into this exponential version, and vice versa. You're going to have times where you have this exponential version and you want to turn it into the log. So just look back and forth at these and track where the variables are going. Excuse me. Okay, so like watch where the b is going. Okay, the base is a subscript over here on the log, but the base is the base over here. Now, people sometimes look at this and they look at this again like it's an exponent. Oh, that's b to the x. No, the B is like a subscript. It's like a note, like a footnote. You ever, if any of you have like read a book, sometimes there's like a footnote at the bottom where like in really small letters, it'll like say something. That's basically all this is. It's a notation. It's a footnote telling us which log we're using. It's log base 2 or log base 3 or log base 7. Right? You have this little what that'll be what your value is down here. So if it's your base over here, so like remember on over here we had a base 2 exponential and a base 2 logarithm. Those have to match up if they're going to be inverses. But see how the 2 is in those two places? Okay. And look at the y. Well, the y over here was the exponent. But over here it's like down on the ground. Yeah, because without logarithms, you can't solve for something when it's up in the exponent, right? It's hard to get at. So the logarithm helps us change that. You'll hear people make the claim and say, logarithms are just exponentials, which I guess you can make that case because here y is the exponent and here y is equal to the log. So yeah, you can kind of say that logs are exponents, but I find that doesn't help students all that much. It can actually confuse them a little bit. But I do want you to see the connection between the exponent y here and the fact that y is equal to our logarithm right here. Okay? And then x, the thing that it's equal to, b to the y, once you simplify that, you get some x. That's just our answer. Right? So let's take a look at this. Let's look at some actual examples, and we'll see that things that look super confusing when they're in the log form, because none of you know what logs are, because I just told you like 5 seconds ago. I'm gonna show you stuff, and you're gonna go, I don't even know what we're looking at anymore. But once you use this definition to convert it back into exponents, you'll go, oh, that's not that hard. For instance, if I was to write the log, so let's say we've got 2 equals, let's make this a 3. 3 equals log base 2, 8. Okay, so if I hand you this, and some of you might be quick. Some of you might be quick studies, and you go, no, that makes sense. I'm looking at it. I understand what that's saying. But I would guess there's a number of you who are a little confused and go, 3 equals log base 2 of 8? What is that supposed to mean? Well, let's use this conversion right here. We started with this. Let's convert it into its exponential form. So this means, well, we've got a base of 2, so 2. Okay, 2 is our base. The exponent up here, that's our y. Okay, well, that's our 3, right? The thing by itself is a 3. So it's really 2 cubed. Okay, so 2 to the third equals, and then it equals whatever x is. Well, here, why does my page keep jumping around? This is annoying. Two to the 2 cubed equals x. So what's the piece by itself? Well, over here in our log, the piece at the end, that's our x. That's an 8. So this whole thing translates to 2 cubed equals 8. But when it's written in that form, you're like, well, yeah, 2 cubed equals 8. That's pretty simple. That's pretty straightforward, right? Yeah, when it's written in exponential form. But once we write it in log form, people get really confused because it's new and confusing, right? That is the number one thing I recommend in this chapter. When you get confused with the logarithm, try to break it down in terms of the like this definition right here, where you're translating it from this log to this exponential. I would say probably half the time that you get stuck in this chapter, just doing that will probably make sense of everything. You'll go, oh, I see it. Just like this. Most people in the class probably pretty confused when they're looking at this. Hopefully, you're not confused at all when you're looking at this. 2 cubed equals 8. 2 times 2 times 2 equals 8. Yeah, that's right. That makes sense. But over here with this log, I'm confused. It's just a different way of rewriting the same thing. Same information in 2 cubed equals 8 is encoded here in 3 equals log 2 of 8. But it's a different way of writing it that we sometimes have to use. You might go, well, why can't I just write it as 2 cubed equals 8? Because we need the logarithms to be the inverse of the exponential function. That's why. That's why we have to do it that way. Okay. So the number one key is understanding the basic definition right here of the logarithm. I see students that don't understand this basic definition of logarithm, but they're moving ahead and trying to do the harder parts of the chapter, but it doesn't work. If you don't understand the basics of what a log is, how are you going to like solve a logarithmic equation? You're not going to. So don't try to plow ahead. Make sure you understand the basics of the logarithm, and then you can move into the more complicated parts of the logarithm. Okay? Like the log properties and solving log equations and stuff like that we'll get to. So let's see, a couple minutes. Okay. And we have a couple logs that are sort of like special. So sometimes you'll see this. Oops. Here's an example. 2 equals log 100. Okay, 2 equals log 100. And you look at that and you go, it seems like something's missing. Is something missing there? Yeah, that's a good observation. What am I missing from my log 100? I'm missing my base. Where's my base? How do I know what base we're using? Is it base 2? Is it base 3? Is it base 10? The answer is it's base 10. So think of it this way. When we write square roots, you know how sometimes we put the index up there? Like if it's a cube root, we put that little floating 3. If it's a fifth root, we put a little floating 5 up there where the index goes. But if it's a square root, we don't write any number, right? Because it's understood it's the square root. So it's like there's an invisible 2 up there. Same thing here. When we don't use a base for logarithms, it's understood that the base is 10. So if no base is indicated, it's base 10. This is because we use a base 10 number system. We have 10 symbols for our numbers. It's base 10. So base 10 logarithms get used a lot. Okay, like the Richter scale. It's a base 10 logarithmic scale, right? Every time you go up 1, you've just increased the severity of an earthquake by 10 times. Okay, so this makes sense. Like, how do we make sense of this? Well, if the missing base is 10, because we always assume that the base is 10 if nothing's written there, then that means that this is really saying that 10 squared equals 100. Which again, not going to impress anybody, right? No one's looking at that and going, what? 10 squared is 100. We all know 10 squared is 100, right? But it seems sort of mysterious and confusing when it's written in the log form. But once we convert it to the exponential form, we understand it much better. This is why, especially in the beginning, whenever you're confused, use this to convert to that exponential form and see if that helps you make sense of what you're looking at. Okay, with that said, that's where we're going to stop. We will discuss next week logarithms and some exponential functions. Early in the week, I'll open up your practice test for you. You'll have your final exam, and then we can go from there. Okay? Anybody who wants to stick around and talk to me in Zoom, feel free to do so. I'll answer any questions. Otherwise, I will see you